Hello, this is Dr. Keith Schubert. This is actually my second video on floating point. The first one is kind of my cautionary tale. So this one we're going to actually talk about floating point and how you actually can see a floating point number, and in the next one we're actually going to do multiplication. The book tends to like to do addition next, but I think multiplication is actually easier. So that'll be kind of our format as we go through. So to consider floating point, we want to deal with non-integer numbers. So very small, very large. If you were to include starting with the radix point fixed and go from there, when you had to deal with something like 10 to the 56 here or something, you'd have 56 decimal digits to get out there. That's crazy. Um, you'd be storing so much stuff that it would be almost unimaginable how much you could have to for decent sized problems. You could easily get into, our floating point numbers, the highest precision we have deals with exponents up to 308. 308 decimal places on there. Um, you know, for every 3 decimal digits, it takes you 10 bits. So, you'd be dealing with 1,000 bits. That's an incredibly large amount of data just to try to hold something. And usually we can only measure things accurately with our various sensors available to usually somewhat, good stuff to 6 decimal digits, and really, really awesome scientific precision measured stuff can get to 9 or a little bit more. When you're doing major scientific things, the best one I know of is our measurements of gravity waves by building a multi-mile long facility. They're getting measurements somewhere around 15 digits, and then using some multiple measurement things they can crank that up a few more digits beyond that to try to get to the precision of gravity wave. But I guess the point I'm trying to get to you on here is just, when you're dealing with this, it's not the type of thing, even, with that 15 digits, the majority of this you'd never be using. You couldn't measure it, so it'd all be zeros. So why store a whole bunch of zeros? That's the idea of floating point. We want to put the precision, all the details of what the digits are, to where the size of the number is. So we only store things that matter. Don't store things that don't matter. Now in binary, they're pointing out that, there's a sign and 1 point, a bunch of X's. This is in base 2, and then since we're doing things expanding scientific notation in base 2, we 2 to some exponent. This is what floats and doubles are in C, and that'll just vary how many, X's and Y's you have available to you. I'll explain in a little bit why we do 1 point and, why we don't have a sign up here, so on and so forth. But just at the moment, just consider that's what it's going to look like, and it just highlights. Make sure you're always using the base as it's going through. This will create a little bit of challenge. We'll have to do some conversion when it goes on, because you have to do this all in binary, but it's all that makes sense for the machine when it's calculated. So the standard that defines this is the IEEE 754 standard. We're going to be talking about the parts that are in the 1985. There's a new update to it, but the new update doesn't say anything to what we're talking on here. It deals with, enhanced precisions beyond this, and a number of other areas. But the basic 1985 standard defines single and double precision and how you have to calculate stuff, and that's as far as we're going to worry about. The newer standard just enhances beyond there. Okay, so the reason why this came together is there was a lot of different standards. Every manufacturer made their own floating point number standard, and they had different precisions and different exponent ranges. So if you were doing any type of calculation, you could never move code between. Your answers were different. You couldn't compare them, and all kinds of weird stuff happens. Some of them were really efficient in areas, and others were efficient in others. And, the underlying libraries, you couldn't transfer those. Um, it was just a nightmare. So they got the best mathematicians, computer scientists, numerics people together from all different venues in industry and academia and got this standard written. And it's pretty much everybody uses it now. Anybody who doesn't use it, I'd be very skeptical of them as it goes on. Um, there was in the early 90s an enhanced version, which has now been wrapped into the more um, recent code that Apple was using, which they called SANE, um, something or other, um, standard Apple numeric environment or something like that, which allowed you to go beyond double precision, and they did some other kind of cool stuff. It was actually very good, but that's one of the only ones that make sense, and everything that was cool from that has been wrapped into the new standard anyway. Um, you know, so it's anybody who's not using, one of the 754 standards at this point, I wouldn't even want to deal with it. Okay, as we mentioned, the single and double precision 32 and 64-bit were defined in the 1985 standard. So that's just as a word of interest to you. The 32 and 64-bit um, size comes all the way from the 1980s. That's gives you an idea of where exactly we've been sitting at this spot. It's pretty efficient, and here we are, essentially 30 years later, and the data from that same standard is still relevant to us today in how we calculate. Okay, so um, floating point numbers. If you want to start thinking about what you would do when you're doing it, let's be even more generic than we had before. You've got a plus or a minus at x dot xxxxx times whatever the base is raised to plus or minus some exponent. And the question is, what matters most? Well, what matters most in what sense? Well, for us, we want to consider things that we have to do quickly and frequently. And one of the most frequent things you're ever going to do is check a number. So when we check a number to try to find out who's bigger, who's smaller, things of this sort, the most important thing you have is the sign of the entire number. If I want to compare two floating point numbers, you flip this sign bit, you have done more than anything else to handle it. If the sign bit differs, it doesn't matter what anybody else is. All that matters is the sign bit. So the sign of the entire number is the most important bit for determining the value of the number that's there. The next one that comes in is the sign of the exponent. You flip that one, you've changed the magnitude. So if this number is the same between two, this plus or minus will have more influence than anything else. If one's plus and the other's minus, you can just look at that one and tell the one that's the plus is going to be bigger than the one that's the minus. Then the magnitude, if both of the signs are the same, the magnitude of the exponent is going to have the biggest effect. Then you can just look at that number to tell which one's bigger. If both of the signs and the exponent are the same, then you look at the magnitude of the significand. Mathematicians call this a mantissa. So this is just a note. If you're a computer scientist, this is a significand. If you're a mathematician, this is a mantissa. In general, most engineers are closer to the computer science end of it, so we tend to use significand. But you can tell people which did they take their numerics course in a math department or computer science department based on which name they use for them. So this is actually why the standard's going to do what it does. It'll take the sign of the entire number, and these two, since they're right next to each other, so this sign and its magnitude are split, but these are right next to each other, so I can just lump them together. So we consider three things: the sign of the entire number, the value of the exponent, because we'll lump those together, and the magnitude of the significand. And that's how we're going to figure out what's going on. Now, since we're going to lump these two together, what I'm going to do is introduce another number encoding, because we want these to be grouped together in an intelligent fashion. And so what we're going to do is we're going to use what's called an excess number. So to kind of introduce why I want an excess number, I'm going to consider just some 3-bit codes. So I've written, the numbers in binary from 0, 1, 2 all the way up to 1, 1, 1. Right? Now, so 0 through 7 in regular binary. And if you notice in binary, as the bit patterns increase, I get a nice increase in the numbers. Now, what happens when I start encoding negatives? 2's complement. As I walk through it, they start increasing nicely, and then it flips magnitude, or it flips sign, and the magnitude goes all the way down to -4, and then it starts increasing again. Okay? So, when you look at this, you've got this kind of weird thing. If you're trying to determine which one's bigger, your negatives look larger than your positives. And so this is kind of a very strange way to stick your numbers in sequence. And it doesn't allow you to easily do a comparison here. You have to do some calculations. So this is not what was chosen to encode the exponents. And this is all due to what we had noticed before, that the sign of the exponent and then the magnitude of the exponent. So we want a way to calculate those in one fell swoop, quickly comparing what the size is. Well, excess numbers give us that ability. What excess 3 does is you store the number, the value of the number plus the excess code gives you the number to store. So -3 plus 3 for excess 3 code means you store -3 plus 3 is 0, so you store 0. -2 plus 3 is -1. Oh, sorry, -2 plus 3 is 1. Wait until I'm tired. So I store 1. -1 plus 3 is 2. I store 2. 0 plus 3 is 3, so I store 3. 1 plus 3 is 4. 2 plus 3 is 5, 3 plus 3 is 6, 4 plus 3 is 7. But it gives us a nice code. Now, the difference between excess 3 and excess 4 is just you add 4 to these. -4 plus 4, 0. -3 plus 4, 1. -2 plus 4, 2, so on and so forth. Theoretically, you could ask, I could then add any excess I want. Yes, sort of, yeah, but not exactly. The standard only allows you to do, for this size, 3 or 4. And the reason is that we have 7. That's our largest number. So you calculate the possible excesses by the value of the largest divided by 2. Well, 7 divided by 2 is 3.5. So you can either do 3, round down, or 4, round up. If you round down, you get a slightly higher amount on the positives. You get up to 4, and you only deal with -3. So it's slightly bigger range on the positives. The excess 4 gives you the same overall range, but it goes from -4 to 3. So this is slightly advantage negatives. In our case, we tend to use more exponents that are slightly larger. So we're going to do the diminished excess. So maximum representable number for that many bits divided by 2, rounded down. That's going to be our excess code. So that's how excess numbers are stored. Now you'll see where we put this, and this is the exponent that's here. They call it, and this is the book's term, they use the term bias. So this is the book's, back to the book's PowerPoints. So for single and double precision, we have 8 or 11 bits. Just consider the 8 bits as it's going in. That's what we're dealing with in here, right? So when you're dealing with the 8 bits that goes on, right, you can get up to 256 55 is the largest number you can represent in 8 bits. So because it goes 0 to 255. 255 divided by 2 is 127.5. So it's 127 is the bias. So if you look down here under their exponent thing, bias equals 127 for single. That's why it does. Maximum number, and away you go. So when you deal with the bias for they actually have a typo in their slides on here. It's 1023 is the bias for, so they typoed it backwards. I'll have to try to remember to send in to them and tell them they got an error in their slides. The reason is you take 11 bits and 2 to the 11th minus 1 gives you the 2048 minus 1, 2047 divided by 2 gives you 1023.5, round down 1023. So 11 bits dictates that it has to be 1023. The excess one in terms would be 128 or 1024, but we don't use that one. We want the slight advantage to the positives. So that's actually where the exponent comes from. So when you store the exponent, to get it back, what you mean in the power 2, because remember it's stored with an extra 127 or 1023, you have to subtract the bias, and that'll give you what the calculating one is. Okay, so that gives you how to get the exponent here. We'll do an example, actually probably a bunch of examples to get you used to it. Now, for the fractional part that comes in, or what we call the significand and mantissa, we're going to deal with 1 plus a fraction. Now, the reason why we want to do this is because when you consider floating point numbers, scientific notation in decimal, you always have something that looks like, 2.3 times 10 to the 5th, or something of that sort, right? The first digit is never a 0, though. It's always a 1 to 9. You could have 1.4, but you can't have, times 10 to the 5th, but you can't have 0.14. And so by rules, that first thing cannot be 0. That means out of the 10 possible numbers that could, be represented a digit for a decimal, you actually end up with only 9 on the first. Now, that's not a huge advantage in calculation. It is a little bit, and cryptographers try to use such things to break codes. But in our case, it's a huge advantage, because when you go to base 2, it's either 0 or 1, and you're not allowed to have a leading 0. That means the leading digit has to be a 1. So since we know it's a 1, why store it? And this is the tricky thing that's is done in the standard. We call this one the hidden bit. And it's called the hidden bit because you don't need to store it, but it's actually there, and it's calculated. And it's a benefit of our standard. So you really get 1 extra bit of precision for free without having to store it. So that's an important one. People often forget to put it back in. So hidden bit, very, very important. So what you'll do is you'll get your number into the form 1 point something or other, and you'll only store the thing after the rate exponent. The 1 is for free. All right, so that's that one. And then the sign is pretty standard. Now this format, -1 to the s, is defined because we wanted to have 1 mean negative. Because in all of our other number standards, a leading 1 always meant it was negative, like 2's complement, signed integers, so on and so forth. Leading 1 means negative. So we're so used to, and we've written so much code to check for a leading 1, meaning negative, that we wanted to maintain that standard here. And then this allows it to be mathematically justifiable. -1 to the 0 is just 1, so it means it's positive. And -1 to the 1, well, that's -1, so that's clearly a negative. So this is kind of the mathematical justification. In single precision, since we have 32 bits, here's 1 bit plus 8, that's 9. 9 off 32 leaves you 23 bits to go into the fractional part. Similarly, 1 bit here plus 11 bits, that's 12. Out of your 64 bits leaves you 52 bits left for the fractional part. So this is the part that determines the precision of your number. Now the first thing we want to do is we're going to take a look at what is the range precision. Now the range precision is going to say, essentially the big and small numbers you can deal with. So that's dealing with the exponents. Now amongst our exponent code, so this is for single precision, so we have our 8 bits. The 000s, these are what are called the D-normals, and I'll deal with that in a sec what it is, but these are predefined. The all ones are reserved for essentially your error codes. This is where you get plus or minus infinity, the not a numbers. Whenever you get those type of codes, they're actually encoded in the numbers, and those error codes are all 111s. So therefore, you only have from 01 all the way up to 11111 0 at the end. So that's what they're telling you here. The exponent, the very smallest I can deal with is 1. Since we're excess 127, 1 minus 127 means the smallest I can ever deal with as an exponent value for single precision is minus 126. To make the fraction as small as possible, I set them all to 0, which means the significand is just 1 point in the fraction, so it's just 1. So putting that back into our number thing, plus or minus 1 times 2 to the minus 126, and they point out to you that that's around 10 to the minus 38. It's a fairly decent number of digits that's in there, and it's a practical, useful range. So that's, cool as it goes. Now, for the largest value, remember, we can't do the all ones, so it's all ones followed by a 0. So that's 254 minus 127. That gives us plus 127. That's our exponent. To make the fraction as big as possible, we put all ones in the fractional part. So that means it's 1.1111111. You're just shy of 2 by a tick. So for approximations, we just put in 2 to make it simple. So you have plus or minus 2 times this, which is pretty darn close to, this 2 is like 2 to the first, so we can bring it in, and it's essentially plus or minus 2 to the 128th. And so that gives us 3.4 times 10 to the 38th. So we usually just say it goes from 10 to the minus 38th to 10 to the 38th is essentially the range we can handle here. And like I said, actually a decent number of things we'll handle here. Usually we have to go above this only when you're potentially multiplying values that are at these kind of range ends, and so we need to deal with larger ones. But we often do have to deal with that. So that's why single precision, even though it can handle the final answers well, sometimes intermediate results don't fit so nicely inside there. When you go to double precision, I'm not going to spend as much time on this because the same exact thing happens. These are called D-normals. These are your error codes. You put in 1 for that, and so the exponent, same thing for the significand. So you just have, plus or minus 1 times 2 to the minus 1022. So that's our minus 308. Do the same thing for putting in everything as big as you possibly can, and you end up essentially going up to 10 to the 308. So that's our potential range that we can deal with of what numbers. Now the precision, which is how many digits we can express, we usually express this in terms of what we call epsilon. Epsilon is the smallest number you can add to 1 that still makes a number bigger than 1, which means there are numbers we can add to 1 which end up giving us 1 as an answer. And it gives us 1 as an answer not because that's true in infinite precision, but in finite precision, it makes such a small difference we can't hold it in our number. If we can't hold it in the number, the computer just merely goes on and doesn't hold it. So it just sees 1 still there. So about how big is that? And so that tells us how many digits we can, in essence, hold inside our number. So that works out, there's 23 bits of precision. So the smallest I can deal with is 2 to the minus 23rd. That's going on. You'll note that I'm not including that leading 1 because the leading 1, it's 1 plus this still makes a difference. So it has to fit in the 23 bits that are stored. And you don't have to worry about the 1. It's already there for free. This is why we define epsilon this way. So we just have the smallest digit that's in there, everything else 0. And they say this is 6. That's reasonable when they're doing it. They're taking the log, but log 2 is not 0.3, it's 0.3 and some change. When you multiply, it does make a slight difference here. Another way that I prefer to kind of show is every 10 decimal digits is 3 digits in binary, and 3 digits in your decimal or in binary. 2 to the 3rd is 8. It's pretty close to 1 decimal digit. So 10 gives me 3, and 3 gives me 1. So this gives me 3 plus 3, 6, plus this gives me another 1, so it's 7. So you are between 6 and 7 decimal digits in reality, because there's a antecipart that goes in, and so it's blah 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 times 10 to the 6th. So that difference, I think it's 7 point something. So it's almost gives you the 7th digit. So 6 digits if you want to be very precise, but that kind of underrates it because you have a little more than that. But anyway, 6 to 7 digits, either of those is fine in my book to say you can hold, because you're at that zone. When you go double precision, remember you have 52 bits, so that's the smallest. This is actually the trick when I was doing that square root area. Remember I took 52 square roots? It's to knock it down so I only have 1 bit left. And when I only have that 1 bit left, I have 1 plus 2 to the minus 52, and then I square that 52 times. So this is where you can see what I was trying to achieve in that one. Sneakily, without being seen, it's 1 plus a really tiny thing raised to that same power. So that is the definition of E. So that's kind of where the program from the previous one was taking advantage of this. We're going to take a look at 52. There's 3 for every 10, so that's 15 plus a little extra, so that gives you 16. So both methods give you 16 digits for this one. And indeed, it's like 2.02 times 10 to the 16th. So as exactly if you want to take a look at it. So you have 16 decimal digits. The increase is tremendous because when we go to double precision, we threw a lot more at the precision part here. And this allows the intermediate calculating numbers to have more digits as a safety margin, which is why we tend to prefer using double precision to single precision if you can afford it. The only area that single precision starts being pushed is GPUs for high performance calculation have a tremendous speed advantage for single precision, not for double precision. So if you can afford to do it in single precision, it really gives you a huge speed up. Okay, so let's do an example. Minus 0.75. So this is, if you think about 3/4 as a fractional thing, so they kind of put out here, but 3/4, this is 1 is 3. Don't worry about the point there for a sec. 1 is 3, so you need 3 divided by 4. Move the radix point over 1, that divides by 2. Multiply by 2 to the minus 1, that also does another division by 2. So this, takes 3. Move the radix point, becomes 1.5. So you divide by 2. Multiply by 2 to the minus 1, that's another 1/2. So this is readily understandable as 3/4, I believe. Minus 1 to the 1 handles the negative sign. So you can see we've kind of written it into our scientific notation in binary. And from this format, it's very easy to turn it into your IEEE standard. So we always want to get it here and then handle it from there. So the sign is 1. The fractional part, we can easily see. We ignore the 1 here, and it's just 1 and then nothing after it, so it's all zeros. So 1 followed by all zeros for the fraction part. The exponent is right here, -1 is what we want. We have to add the bias in. So you're either adding 127 for single precision or 1023. So you either store 126 or 1022. 127 is 0 and then all ones, and 1023 is 0 and then all ones. So that's kind of nice in their areas. So since it's -1, you just knock off the last bit. So therefore, putting them together, the 1 carries down on both. And then we have 0 followed by a bunch of 1s and a 0, either 8 total or here for 11. And then the fraction part comes in at the end, and it's 1 followed by zeros. 1 followed by zeros. And the dot, dot, dots, either for 23 or 52 total in that portion. So this gives you actually what the computer has as its codes for those. So we can look the other direction. That's one way. How do you encode them? The other one is when you look at it and say, what is this? So we can see the leading 1 here. That means it's a negative number. When you take a look at this is the exponent parts. It's excess 127. So you can actually go in and do what the book does here. They say, oh, it's 129, and so 129 minus 127. That's true, but if I'm looking at this real quick, all I do is I start with the all ones, and I go, well, look, to roll it over, that would be +1. And then to add this one, +2. So this is 2 above 127, which is what I'm doing. So it's just counting up from there. So I can just look at this, though, and tell that's 2 bigger, which is a nice advantage. And yes, if that doesn't make sense to you, by all means, write it, convert it to a number, or do the subtraction. But if you notice what I was saying here, you can just count the sequence, and most examples we're going to deal with will be fairly close. So for book type examples, that's a nice little trick to do. And then for this, it'll just be 1 point. What's here? Well, that's just 101, and that's all zeros. So that's again. Oh, sorry, that even that 1's not there. I didn't notice that was green. So it's 1.01. So 1.01. 101 is 5. So it's 5 over 4 because 2 places pulled in here. So that's 1.25. So 1.25 is our float. So we've got -1 times 1.425 times 4. Well, we already said this is 5/4 times 4, so that's 5, so -5. So that's how you can kind of read the numbers in backwards. I've mentioned that the normals, that's when the exponent's all zeros. For the denormals, the hidden bit is 0. And the reason why we did this, if you don't do that, you can't represent the number 0. Since we're always assuming there is a positive number, 1, that leads it, 0 is not representable, and 0 is a pretty important number to us. So we needed to get something that would allow us to actually get 0, and that's what the denormals do for us. There's also kind of a hole in our number system. There's a very high precision. If you remember, we were looking at there's 7 decimal digits, but so the step size is really tiny, but there's a gap around 0 that's much bigger than that. So therefore, we look at that and we go, well, I don't have a nice fill-in. So this allows us to fill in that space and do 0. Of the two, 0 is the much more important, though. So the only difference for these, it follows the same pattern. This is our negative. We just don't allow the hidden bit anymore. So that means you get 1 less digit of precision, but you get 0, so that's worth it. So that's only for these very small sets. And we only put the minus a bias. So the smaller than the normal numbers, they allow us to handle underflow when it goes in, and they allow us to represent zero. So that's the real key things. If the fraction part is zero, this is where we get the value of zero. Now notice you've got 0 plus 0 times 2 to the minus bias that goes in, but this is 0, so that gives me the 0 area. But I have this sign, minus 1 to the sign, so I technically have plus or minus 0. So you'll often see in calculations plus or minus 0 that comes in. Well, this is why, because this part here essentially blows out your exponentiation here, but the plus or minus part remains. And the reason why we care about that, I could wipe that away too if I really wanted to. But when you're doing limits of numbers and you actually run out of precision, the side you got it from can still be helpful. So there's two different ways I can represent 0, and how I calculate that becomes important. So final area we need to talk about are the infinities and not of numbers. If you remember, that's when we had all the 1 codes. The infinities are when the fraction value is 0, and that encodes plus or minus infinity. Again, the plus or minus comes from the sign bit. So this can, the neat thing is you can use this as calculations go on. You can stick the infinities in there, and according to the IEEE standard, they work as if you had, or as close as we can do to if you actually had a true infinity there, what it does to stuff. Now that doesn't mean you always get a decent number off it. Infinity times anything gives you infinity. Well, if you think of this as an error code, it just means you have an error code stuck in there. But you can keep doing calculations and it doesn't blow up in your face, and you can look at the error code later and then determine what you want to do to recuperate where that came from. But it doesn't cause your program to halt when that goes on, and that's really annoying to have your program halt. It's annoying when you're just working with it, but imagine if your program halted and what you were dealing with was a navigation system on a plane or a rocket. These errors have actually happened where things have halted, people didn't handle it right, and rockets have exploded, and planes have lost navigation system. About 15 years or so ago, a U.S. naval warship off just outside of one of the major Navy bases on the East Coast in Virginia had a problem with an infinity that was calculated, and it ended up sitting there in the waters off the shore for, I think it was like 20 hours or something, until they got the software patch fixed. But the whole ship was just taken down because the computer system crashed, and they couldn't control a reboot because all kinds of other issues. So this became a very big issue. Same exact thing happens when you go, the fraction's not 0, it's the not a number code. So if you've ever seen those NANs, it tells you there was some illegal or undefined result. Whatever the fraction is tells you how it got there. And it can be used in subsequent stuff. So that gives you your rundown of how these work, and hopefully that helps out, and I will see you on Monday.